Hello everyone, my name is Ira Febrianti. I'm from Department of Medical Technology, Institut Teknologi 10 November, Indonesia. And today I am pleased to present a research entitled Automated 5-Grade Classification of Knee Osteoarthritis using a Lightweight Vision Transformer, a Comparative Evaluation. And without any further ado, let's begin with the background of this study. Okay, so knee osteoarthritis is one of the most common degenerative joint disease affecting more than 374 million people worldwide. And clinically, disease severity is assessed using the Cochrane-Lorenz grading system, ranging from grade 0 to grade 4. And however, manual grading is subjective and time-consuming. And existing deep learning approaches are still dominated by CNN-based models, while class imbalance and limited model interpretability is remain major challenges. So therefore, in this study, we compare four lightweight vision transformer architectures and integrate interpretability AI techniques to improve both classification performance and clinical interpretability. Before conducting the study, we reviewed previous research on automated KOA classification, and most previous studies primarily evaluated CNN-based architecture, such as ResNet, DenseNet, EfficientNet, while only a few investigated lightweight of vision transformer. In addition, class imbalance was rarely addressed, particularly for the severe grade 4 category. And existing studies also provided limited explainability or interpretability, making it difficult for clinicians to understand how predictions were generated. And to address these research gaps, our study makes three main contributions. First, we provide a fair benchmark of our lightweight vision transformer architectures. And second, we mitigate class imbalance using gain-based oversampling. And third, we improve clinical interpretability by combining ScoreCam and Lime, and followed by qualitative validation from a radiologist. And for this study, we use the Osteoarthritis Initiative ROAI dataset, which contains 9,786 knee X-ray image labeled according to the Cochrane-Lorenz grading system from grade 0 to grade 4. And the dataset was divided using stratified sampling into 70% for training, 15% for validation, and 15% for testing. As shown in the class distribution, grade 4 is highly underrepresented, accounting for less than 3% of the dataset. And therefore, count-based oversampling was applied only to the training set to address class imbalance while ensuring a fair evaluation. And before training, all image underwent several preprocessing steps, which is first, the image were resized to 224 by 224 pixels and normalized to ensure consistent input for the vision transfer models. And next, we also have data augmentation, including horizontal flipping, rotation, color jitter, contrast, and brightness adjustment was applied to improve model generalization. And finally, to address the severe class imbalance, we use scan-based oversampling to generate additional grade 4 image. And the synthetic image were qualitatively validated by a radiologist before being included in the training set. Okay, we'll move to this slide. This slide is summarizes of our overall research framework. The workflow begins with pre-processing of the knee radiographs, and the processed image are then used to train for light vision transformer architecture under identical experimental settings. And after training, each model is evaluated using several classification metrics, including accuracy, precision, recall, advanced score, specificity, and coherence kappa. And then finally, we apply ScoreCam and Lime to visualize the regions that influenced the model prediction, allowing us to compare not only performance but also interpretability. Okay, in this study, we compare for light vision transformer architecture, The first model is Tiny, which combines convolutional operation for local feature extraction with self-attention. And the second model is Efficient Farmer, designed to achieve transformer level performance while maintaining computational efficiency. And the third model is Tiny, which progressively aggregates information from local regions to global context through focal modulation. And finally, Small integrates spatial attention and general attention. This for architecture were trained using exactly the same dataset, preprocessing pipeline, and hyperparameter to ensure a fair comparison. And then this slide presents the experimental of our work. Uh, Among the four evaluated architecture, Davidan achieved the best overall performance, obtaining an accuracy of 81.10% and the highest count kappa, a value of 0.8958, indicating excellent agreement with the ground truth levels. Now looking at the percast metrics, grade 1 achieved the lowest advanced score. This is expected because early stage osteoarthritis often shares very similar radiographic characteristic with normal knees. So it's making a differentiation is difficult even for experienced clinicians. And then here are the confusion metrics also shows for the Tiny. And overall, these results demonstrate that Tiny provides an effective balance between classification performance and computational efficiency. To further evaluate our approach, we compare our best performing model with several previously published studies. Despite using a light precision transformer architecture, our proposed approach achieved the highest reported accuracy among the compared methods. This demonstrates that a lightweight fission transformer can achieve competitive performance while requiring fewer computational researches than many conventional deep learning models. And then besides achieving high classification accuracy, interpretability is also essential for clinical adoption. Therefore, we used both ScoreCam and LIME to explain the model prediction. ScoreCam highlights the region where the model focus is its attention, particularly around the joint space narrowing and osteophyte regions. Meanwhile, the LIME identifies the local image regions that contribute most to the final prediction. And after a qualitative evaluation, a radiologist confirmed that these highlighted regions were anatomically meaningful and clinically relevant. And then in conclusion, this study provides a comprehensive comparison of four light vision transform architecture for automated 5-grade knee osteoarthritis classification. And among the evaluated models, Tiny achieved the best overall performance. And in addition, can-based oversampling is effectively address severe class imbalance during training, while ScoreCam and LIME enhance model transparency through clinically meaningful visual explanation. Nevertheless, our study has several limitations. We used only a single public dataset, and the generated synthetic image were evaluated qualitatively rather than quantitatively. Therefore, future work will focus on external validation using multi-center dataset and quantitative evaluation of synthetic image quality. And we believe this improvement will further increase the robustness and clinical applicability of our purpose framework. That's all from me. Thank you for attention.